I think I better start because it's already a couple of minutes late. People can join. There's already a question. Can we say that achronal surface embedded in Minkowski spacetime is a null hypersurface? No, we cannot say that. In fact, quite the opposite. Okay, I mean, a null surface can be achronal, but in general, it's a space-like surface, no? And in the achronal is still an additional requirement. Achronal means that it's first of all, so let me just recall the definition I gave. Suddenly lost my notes, excuse me. Achronal has no pairs of time-like separated points. So all pairs of points are either space-like or null separated. So no, we can, in Minkowski, it can be a null surface or it can be a space-like surface. Okay, let me start now. Good. So where are we? So today, well, before I tell you what we're going to do today, let me just say that in the last two lectures, we discussed causality in some detail. We discussed, to be precise, the causal future, causal past. Causal always means time-like or null. So, in fact, if you look in Hawking and Ellis's book, they often use the word non-space-like. So non-space-like is the same as causal. The chronological future, however, is specifically time-like future, and similarly for the past. Then we talked about causal diamond, which is like the overlap of the causal future of a point and the causal past of another point. Then we talked about achronal sets, which I again defined just now. Basically, no pairs of time-like separated points. Then we discussed endpoints and extendable and inextendable curves. And then we discussed Cauchy hypersurfaces and defined globally hyperbolic spacetime. And in that context, we discussed the future and past domains of dependence of any set. And the idea was that for any set that is already achronal and in fact space-like, its future domain of dependence and past domain of dependence together, the total domain of dependence, is the whole space-time that it can access. So if that surface is a Cauchy surface, then the domain of dependence is the whole space-time. So this is all just restating everything we discussed. And then we gave a few properties of globally hyperbolic spacetimes. And today we are going to actually start with a theorem on compactness. And because of this theorem, I will actually say a few words specifically about compactness as a topological notion. I expect you would have read about it, but I think it doesn't hurt to go into it in a little detail because it's a little subtle. Okay. And the compactness of interest today is going to be compactness of the space of paths. And that's a weird space. So we better understand that space quite well. Now, before I start giving definitions, definitions and theorems, I want to point out something historical. So here's a historical digression. And it helps for two reasons. One is it tells you the interdependence of different things that one can define. And the other is that it might help you read different references on the same thing. So there were different definitions of globally hyperbolic. And we've used one, but there are two others. And let me give names to each of these in the historical order. So D1 is And don't ask me questions here because I'm going to define anything which I haven't defined here in detail below. But I'm just giving you a kind of global picture. The space CPQ of causal paths from P to Q is compact. Now, this definition was given by Leray in something like 1952. And the reference I've seen to this has to do with some IAS lecture notes or something. So, but I don't know, maybe it's published somewhere. This is definition 1. Okay. And there's a little caveat to this, plus strong causality. Definition 2, which will be more familiar to you, there exists a Cauchy hypersurface as through which all inextendable curves pass. And this definition is the one we gave last time. And from what I could make out, this definition is due to Gauss, who was a leading theorist at Chicago, relativist. And then there's definition D3, which says the causal diamond DPQ is compact for every P and Q. And again, here there's a little side comment saying plus strong causality, which I haven't yet defined, and probably I won't be defining. So now this definition is generally said to be due to Hawking and Ellis. Now, I could be wrong about who exactly it's due to, but it's these are the definitions used in these 3 sources, Leray, Gauss, and Hawking Ellis. Now, the interesting thing is that they are all equivalent. And when 3 definitions are equivalent, it means you can pick any of them as your definition and the other 2 become theorems. Okay, and this is an important thing to realize. So I hope this point is clear that each of these properties, D1, D2, D3, is a statement of what is a globally hyperbolic spacetime according to that person. So Hawking-Ellis will say a spacetime is globally hyperbolic if the causal diamond is compact for every P and Q. And Leray will say that it's globally hyperbolic if CPQ is compact for every P and Q. And Gauss will say it's globally hyperbolic if there exists a Cauchy hypersurface. Okay, so we have started our life with definition D2, and therefore this is a theorem which we'll prove today, and this is another theorem which we'll also prove today. Okay, but if you read, and this is Wald's approach, so Wald strictly follows Gauss's definition and proves D1 and D3 as theorems. If you, however, go to Witten's light rays, he agrees with that, but he takes a slightly different perspective. He starts with Minkowski spacetime. Now, in Minkowski spacetime, if you just think a little bit, 2 of these 3 definitions are completely obviously true. Which ones are they? Let me see how the audience is doing. Which 2 of these 3 are obvious in Minkowski spacetime? Come on, audience. Few answers to my questions, please. You may need to unmute, or you can type the answer in the chat. You can raise your hand, whatever you like. 2 and 3 are obvious. Absolutely correct. Everybody agrees. D1 is the most unobvious because it's a statement about compactness of a space of paths. A space of paths is an extremely difficult thing. But the fact that Cauchy hypersurface exists in Minkowski space is trivial because you just take it to be t equals 0 horizontal line, that's a Cauchy hypersurface, over and done. So Minkowski space is globally hyperbolic. The fact that the causal diamond is compact is also obvious because you can draw the causal diamond. Here's P, here's Q, and you have here, and you have these light cones. Let's put Q here. And this is the causal diamond. And remember, causal includes null rays. And that means that these parts of it are included. And that's basically enough. That makes it closed. And if it's closed and it's clearly bounded because you can see it, there's a metric in which it's bounded, which is the Euclidean metric that I used to draw it. And so it's certainly compact. Okay. So this drawing says D3 is obvious for Minkowski. So D2 and D3 are obvious for Minkowski. And what Witten does is that he proves D1 for Minkowski at first. And that's good because you start to get an idea how to prove a more difficult result in a very simple space-time. But then once he shows that, he sort of tries to, explain that these are all basically equivalent definitions. And eventually he settles on D2 as the definition. Yeah. Does a causal diamond work as similar as a Penrose diagram? No, a Penrose diagram is much more non-trivial. We will introduce it. We haven't introduced it, and I'm not assuming you know what it is. A causal diamond is much simpler than a Penrose diagram. A Penrose diagram involves what is called conformal compactification, but in a causal diamond, what you see is what there is. This is the actual part of space-time that's in the causal diamond between any point P and point Q. Of course, what I've drawn is for Minkowski, and obviously for a weird space-time, it might be metric, it might be difficult to draw, but causal diamond is a simple notion. Penrose diagram is not a simple notion. Also, a diamond and a diagram cannot be the same thing. A diagram is a way to represent a situation. A diamond is an actual subset of the space-time. Okay, please don't confuse diamonds or futures and pasts with a Penrose diagram. The diagram is only a method to show you something. It's not a system. It's not a space-time. It may be a representation. Actually, what it is a partial representation or representation capturing some features of space-time. And please do not confuse them. They are not related. Okay. Although, of course, both rely on causality. Good. Okay, so therefore now what is our task today? It is to prove these two, D1 and D3, and while proving them, I'll also state them more carefully. Okay. So now, from now on, globally hyperbolic, as it was last time also, globally hyperbolic will mean exactly D2. Okay. Good. All right. Now, what we are going to do is to take a point P in a globally hyperbolic spacetime and take a point Q that is in J plus of P. So it's in the causal future. So it could be either time-like separated or null separated. But I'm going to just take it quite generic. So it's okay to assume for now that it's time-like separated. And there will be, well, actually, you don't have to assume that. And there will be curves which connect P and Q and some curves. And we are going to try and find some properties of this space of curves. Now, you see that the curves I'm drawing, they're dangerously close to not being causal, but they're supposed to be causal. So what does it mean for the curve to be causal? Well, let's draw an example of a curve that isn't causal between the same points. I'll erase it later. Okay, maybe I can draw it on the same diagram in a different color. Imagine this curve. This curve is not causal. What's wrong with it? Well, this part is space-like. As long as the angle, the slope, is less than 45 degrees, it's space-like, and so this is not causal. Okay. You can also see likewise that any curve which does zigzags like that is not going to be causal. A curve which also goes there and comes back, you may think this is okay because we could try to make most of it vertical, but you see, in order to turn around from here where it's going up to here where it's going down, there will be some portion in between where it's again space-like. So all my yellow curves here are not causal. All my blue curves are causal. Okay, this blue curve might worry you, and that's just my bad drawing, but the slope should be always at least 45 degrees and steeper than that. Okay, so I hope we got the idea of the space of causal curves. So now this space, that is the set of all these curves, is what I'm going to call CPQ. So, so this is a set of all curves. Let's call the curves x mu of S such that x mu of 0 is P, x mu of 1 is Q. And there's one thing which it isn't necessary to say too often, but I'll say it anyway. Under reparameterization, we identify the curves. They're identified. So although I'm making it look like I'm defining the curve in some coordinate system, and that's usually necessary to define a curve, but I'll say that, well, if your curve and my curve are the same in two different coordinate systems, then I'll just call it the same curve. Okay. Now, set of all such causal paths from P to Q. I'll just give it a name. I'll call it C lower P upper Q. Okay. Now we are going to talk about the space. So we can call this set also a space. But when you call a set a space, you're assuming that it has a topology. Okay. A space should always mean a topological space. And in order for there to be a topology, we should define that. Okay. The first thing to realize is that the space of paths is not any finite dimensional space. It's actually not anything very simple, because you see, I have infinitely many points along each path, like this, and I can vary each of them independently except the endpoints, and I'll get a new path. So that's infinitely many variations I'm allowed to make, but I should at least keep these paths continuous. If I randomly vary one point in the middle of the path to somewhere else, then the curve will break. So I should keep it continuous. I might want to keep it smooth. So it's not as simple as just saying it's the space of all those points, but you can see from this that it's basically infinite dimensional. So it's quite a beast, but it's not as bad as we might think. And one of the facts about it that makes it not so bad is that it's compact. And we are going to first define a topology and then give the argument that in that topology, it's compact. There are going to be moments when I'll give something more like a sketch of the argument. It's going to be in many pieces. I'm going to take up a bit of time, so be prepared. Probably this is one of the toughest things we are doing till now. Okay. Good. So what's a good topology? Let me define the topology on this space, and then I'll pause for questions. So the idea is that we are going to borrow this topology from the topology that we already know for the space-time M. Borrowed from topology of M as follows. Knowing the topology of any space is basically specifying a basis for its open sets, and the basis has to satisfy certain properties, and then any union of basis elements is again declared to be an open set, and any finite intersection of basis elements is again declared to be an open set. So what we'll do is the following. This is M. Let's take a U, which is an open set in M. And since we've already chosen our starting and ending points P and Q for our curves, we'll already assume that P and Q are in U. So we'll only pick those open sets that contain both P and Q. Okay. Now we'll define O of U to be the space of all paths from P to Q, all causal paths from P to Q, such that the whole path is inside U. So, for example, this is a path in O of U. This is a path in O of U. Okay, but this, okay, now my drawing is really bad because what I need to do, let me try drawing a little bit bigger and try to make this a little better. Sorry, I apologize. Need to be quite a bit bigger. And then let's get rid of, oops, get rid of this stuff. Yeah. Okay, good. So let's try again so that I can actually show you parts which are and which are not in U. So let's first pick P and Q. Here's P. Here's Q. Okay. Now I have to take an open set that includes both P and Q. So let's take one which looks like this. Okay. Now you see that in this set, these three are causal paths. But here's a path which is perfectly causal. Whoops, come on. The software sometimes chooses my lines to be straight. Okay. Here's a path which is perfectly causal, but is not contained entirely inside U. This is U. You see that? So this path is not in O of U. Okay. And so O of U is a set, is the set of all paths which lie entirely in an open set U of M. This is M, of course. And what we'll do is declare O of U to be a basis for a topology on the space of paths CPQ. So O is also a space of paths, but it's a subspace of paths. That's pretty clear. It's given all the causal paths from P to Q, and given an open set U, it's only that subspace which is fully inside U. They don't stray outside. Okay, so clearly O of U is a proper subset of CPQ, and I call it an open set, and then I say that, well, now this is a basis, so take any unions and intersections, finite intersections, arbitrary unions, and all of them together will be the open sets, and the set of open sets defines the topology. Shouldn't the space traced out by the causal curve in the physical space be equivalent to the causal diamond? Yes, this is true. This is true, but it's not CPQ. As you said, not CP. So that much is correct. Yes. So the space inside which these causal curves live is DPQ, the causal diamond. But here we are talking about the actual space of curves, where every element of the space is a curve. Okay. It's a much more abstract space. Yeah. But I think this is correct, that basically as you vary over all causal curves, you basically have to be in the causal diamond. Okay. But even in the causal diamond, you can find, you see, here's the reason why this is not useful. Even within the causal diamond, I can find non-causal curves. Okay. The causal diamond is the space traced out by causal curves, but it's not the other way around. Let's just show you that, just so that you're very clear. Here's the causal diamond of P and Q. Always draw Q too far. Here's Q, here's P. So like that. And now I can always have a curve which goes here for some time, and then it does this, and then it goes there. This is not a causal curve, but it's fully contained in the causal diamond. Okay? Yeah. Okay. What if only finitely many open sets of M contain P and Q? Well, remember, M is a space-time, so it's actually a differentiable manifold. In a differentiable manifold, this won't happen. If you could, I suppose, take M to be some arbitrary topological space, and then you could still talk of continuous paths from P to Q in an arbitrary topological space, but that's not what we are doing. So we are always starting with M being a differentiable manifold. Okay, and that's this is a key point, because a differentiable manifold has a concept of dimension. So when we say space-time is 2 or 3 or 4 dimensional, we are making a topological statement which cannot change under reparameterizations. 4-dimensional is always 4-dimensional. So here M in our minds is always 4-dimensional, maybe 3, maybe 2 if we want to do a simple example, but really 4. Okay. And it has infinitely many points, but that's not all. It's actually homeomorphic, that means topologically equivalent to a subset of Euclidean R4. Okay, the fourth power of the real line. And so that's very important. Now, the space of paths in that is going to be you cannot associate it to any finite dimension. So it's probably not even, doesn't even count as a differentiable manifold. Maybe it is, but certainly it's very hard to think of putting a metric on the space of paths, a metric with proper positivity. Yeah. Okay. Basis has to span all the paths in CPQ. Yes. And OU will span all of them. O of U may exclude some causal paths, but there'll be another U, right? So O of U, okay, as U, I should have said this, but I thought it was clear. The set O of U, okay, let's just do this. I'm glad you're asking. These things, it's always best to clarify. U open set of M. So for every open set of M, I declare O of U to be an open set of CPQ for every. So one U will obviously miss some paths, but I'm going to do this for every U, and that will cover everything. Yeah, thank you. Thanks. Okay, Rahul is happy. M has the usual topology as R4, yes, and always does have. Yes, absolutely true. So I hope this point was quite clear, and thank you for the questions, because they communicate to me that we are quite on the same page, and I'm really happy about that. Okay, so we define a topology. We take let's say it in words, we take every open set U of M containing P and Q. There will be some that don't contain P and Q. We ignore those, or we can add them, but they'll just give us empty results. And then we look for all paths which stay entirely inside that open set, and we call the space of such paths to be an open set of CPQ, and then that space of such paths O of U, when we vary U over all open sets of M, or at least over a basis, then O of U will give me a basis of the topology on CPQ, and it will cover CPQ. Good. So we define the topology. Now comes the theorem. With this topology, CPQ is compact. Okay, and we're going to spend a lot of time. Actually, I don't know, I naively thought we might do this in the first half an hour or 40 minutes of this class, but it may not happen. And whatever happens, I'm not rushing through things. So we are going to do this properly. Okay. I feel that going through the proof of this is probably more than anyone would need in real life. But, once in your life, why not? I mean, it gives us some confidence that we sort of understand what's going on. Okay. Now, before the proof, we make a comment. CPQ only included causal paths. But we could also talk about the space of all paths. And without that, CPQ would not be compact. And this tells us something a little bit fun. There's no analog of this theorem in Euclidean signature differential geometry because there's nothing like a causal path. And so if you want to consider the space of paths from P to Q in a Euclidean signature manifold, like a sphere or something, is just not compact, and that's the end of it. The fun is that here, because we have causality and we have that concept, it turns out the space of causal paths is much more constrained, and it turns out to be compact. Okay, so first let's show that this space of not causal paths cannot be compact. And what is compactness? So I'm going to do this in two stages. First, I'll just say that compactness roughly has to do with convergence to a limit. And so if I can find for you a set of paths that don't converge to a limiting path, then I can right away say my space is not compact. While for causal paths, the claim is that if you find any set of causal paths, then it will converge to another causal path. So that's what we're trying to show. But this counter example is given by the following space. So consider x equals sine of pi and n pi. Okay, consider, yes, sine n pi t and y equals z equals 0 in Minkowski. Okay, so at t equals 0, we are at 0, and at t equals any integer, we are back at 0. So these are clearly not causal paths. Okay, so as a function of time, so I'll just ignore y and z because they're not doing anything. And basically what happens is that you oscillate sinusoidally like this into the future. I hope that's clear. Well, apart from my awful diagram, it's the sine curve, but it's put vertically, which is something we are not used to. And you can clearly see that because of its wiggling, it is space-like in some regions. Okay. So for example, this region are space-like. So it's definitely not a causal curve. Now let's take the limit. So this is a family or a sequence of curves. So this is xn and yn and z. So y and z remain at 0. Xn is this. Now you can see that as n goes to infinity, there's no good limit. No limit. Because the curve just gets wilder and wilder. Okay. If n is very large, then the curve is going to basically zigzag like this all the way. And that's not a limit. Okay. So we've shown, basically, this is actually enough to show that the space of, so we've shown this, that without causality, this space had no chance of being compact. Okay. But I didn't get into, gory details, what is compact. And so let's do that now. What does compact mean? So first, let me write down for you the official topology definition. A subset S, this is true for any topological space. Is compact if every open cover admits a finite subcover. What's an open cover? Open cover is just a union of open sets. So I can write it as U over some I, some index I of UN. I'm sorry, everything looks like U, but the union symbol should be different. Should be able to understand that it's different. So it's a union of open sets, union over UN, some selected ones, not all. If you took the union of all open sets, you get the whole space, not a subset. So, but by taking a union of some open sets, you get a subspace, and it's a cover if that subspace obtained by taking the union contains S completely. So S is a subset of that union. Okay, that's an open cover. Okay, finite cover, finite subcover. It's very important what a finite subcover is. Given a cover, because it's a subcover, right? It's not just a finite cover. A finite cover is easy. It's the same thing that I wrote, but n runs over finitely, many values, no big deal. But a finite cover, a subcover is given un, pick a subset of n values, values of n. That also leads to a cover. Okay. Is this going okay so far? So it's very important that you have, this is for every, so it means you pick your most nasty friend or enemy, ask them to find an infinite cover, and then you have to hunt in that infinite cover to see if any part of it is a finite subcover. Okay. And if you find that there is one, you can't declare victory, because now you have to go to the next enemy and ask them to find another infinite open cover and hunt in that one for a finite subcover. And after you have exhausted all the possible people that you know who know how to find an infinite cover, or that means you have exhausted all infinite covers, only then you can declare victory that this thing is compact. So as you can pretty much see, this is not something that we can readily check. And in fact, we rarely check compactness by classifying all open covers and then looking for finite subcovers. Rather, we use it to generate examples, and we also use it to generate theorems, which then we use to actually verify compactness or otherwise. Yeah. Subset has to have finitely many elements. Now wait, a subset of what? The subset of values of n. Yes. Yes. Thank you. I forgot to write. I keep forgetting to write things. Thank you very much. A finite subset of values of n that also leads to a cover. Exactly the point. Okay. Now examples. Okay. So let's take R2 with the usual topology, just the plane. And in this thing, we can draw a disk. And we'll draw the disk mod x less than 1. And we'll ask if this is compact. Okay. Now, the first thing that you can immediately see is that there's certainly a finite cover. For example, this disk is a cover. It's just a bigger disk, and it clearly covers our original disk. So finding finite covers is no big deal at all. Okay, and yet it doesn't tell us anything about compactness. Now, our friend who is specially qualified at providing difficult infinite covers provides the following set. This friend says, consider Dn, the open disk, all open disk at the origin. So the origin with radius Rn equals 1 minus 1 over n equals 2, 3, all the way to infinity. So this cover is clearly infinite, and it has disks of radii 1 by 2, 2 by 3, 3 by 4, getting bigger and bigger. Okay, now if this original set we called S, this is this one, the space of everything with x mod x less than 1, then in fact the union n equals to infinity of dn is S. So it's a cover. It's an infinite cover. Okay, and it does cover S. Now you might be worried about what it means when I say it covers S, because it's a set of expanding disks and none of them by themselves covers S. Okay, it's only when I take this infinite union that it covers S. But there's a very precise way to check. Okay, and let's do it because I think, again, it might be helpful to you. Pick any point x in S at a distance. Now, to be in S, this x has to have a distance mod x less than 1. So let's pick at a distance mod x equals x0, some number less than 1. Okay, so I have to do that first. Now, if I can show that this arbitrary point I picked in S is in my cover, then it's a cover. Okay, because I picked an arbitrary point and checked whether it's contained in the cover, and it certainly is, as we'll show in a second. So now all disks dn for n greater than something, n greater than 1 over 1 minus x0 will include my picked point. Let's call this point x0. Will include the point x0. Therefore, it's a cover. Okay. And pictorially, if I picked a point inside here, if that point was somewhere, say here, then of course, say here, then of course the open disks which are bigger than that will include it. Okay, and therefore in the full union, it's included. And that's the point I was trying to make. Okay, however, there's no subcover. No finite subcover. There are infinite subcovers. You could take all disks starting, you could take n to start from anything other than 2, like 3 or 4 or 10 or 100 or million, and it's still a cover. Okay, but it's never a finite cover, and there's no finite subcover. And therefore, we conclude that mod x less than 1 is not compact. So proving non-compactness is relatively easy because you just need to find one infinite cover which doesn't have a finite subcover. Proving compactness is harder. Okay. Now there are, okay, let's note also that however x less than or equal to 1 is compact. What goes wrong in the previous proof is the following. Supposing I add this boundary here like this to it. Now I can pick a point on that boundary, and there's not a single open set in this union which contains that point. Okay. So this isn't an open cover anymore. Dn are no longer an open cover if I add this boundary in. And now, okay, that's not a proof, that just shows that previous thing broke down. But now you have to show that every open cover of this disk, closed disk, and this, if I call this one S, oops, then this is non-compact, and this one I'll call S bar, and it is compact. Okay. Now, it's, as you can see, it's still difficult to prove compactness, but there's a very famous theorem called Heine-Borel theorem, which says that every open cover admits a finite subcover. This property is equivalent for a subset of Rn only to closed and bounded. So if you're dealing with subsets of Rn for any n, that is n copies of the real line, Euclidean space, Minkowski is also fine because Minkowski has the same topology as Euclidean space. It may have a different metric, but in any metric, actually, you can talk about this in any Euclidean signature metric, because bounded doesn't make any sense in a Lorentzian metric. Bounded means the set of all points at some distance less than some starting point, and that boundedness requires the metric to be positive so that there's a sphere. Okay. So these two properties are equivalent as per Heine-Borel theorem for a subset of Rn. And the second thing is very easy to check. Closed means contains its limit points, I explained last time, and bounded means bounded. Bounded means basically there's some box in which the whole set is contained. And now we can see what goes right or wrong. So if we look at this disk, x less than 1, it's not closed. It doesn't contain its limit points. Its limit points are the points on the boundary. And therefore, by this theorem, it's not compact. So I didn't need to find any open covers. If I consider the same thing, but with x less than or equal to 1, it is closed. Both are bounded. They're bounded literally in the sense that if you like, the distance, pairwise distance between them, or the overall, you can basically put them in a box. I think, just saying that is good enough to say bounded in a metric space. So it's clear that they're bounded. Now you can think of a third example also in R2, the underlying space we have taken here to be R2. The third example is the infinite open interval, viewed as a subset of R2. And this is basically all points x comma 0 for all x. Okay, now this one is closed because take any infinite subset its limit point will also lie on this line somewhere. So it certainly contains its limit point. So it's closed, but it's not bounded. Okay, this is R1 inside R2. And therefore, this is also not compact. So you can see that between closed and bounded, if one fails, then it's not compact. Here, this is compact. And here, it is not compact. Okay, so I hope this gives you the idea. Yeah, from Minkowski space, can we take bounded to mean each of its coordinates is bounded? Yes, we can actually. And that's what we would do. Or we could say that the sum of squares of the coordinates is bounded, which is the same thing. But then we take the sum with all positive signs. We don't take one term with negative signs. Exactly right. Good. Okay, so we got some clarity about this. But unfortunately, CPQ is definitely not a subset of any Rn. And now it turns out that we can also extend this theorem more generally to metric spaces, but it's also not clear what sort of metric makes sense on CPQ. Remember that the definition of a metric, a real actual metric, not a pseudo-Riemannian metric, but a Riemannian metric, says that you have a unique distance between any two pair of points, which would be here any two curves, but that if that distance is 0, then those 2 points are the same. Okay, so if two curves are identical, point for point, all the infinitely many points overlap, then our metric would be then and only then our metric would be 0, and you'll begin to realize that it's a very tough task to try and fix a metric on this, which satisfies all those triangle inequalities and all the rules for a metric. Okay, so this is not going to help us. Luckily, there are other definitions of compactness. And amusingly, it's very much like the history of globally hyperbolic, which I started with, where I told you that there were 3 definitions at different times. Turns out that there were different definitions of compactness also. And the one that we have been using, every open cover admits a finite subcover, got adopted universally only in relatively recent times. Okay. Now, for these details, okay, so let's look at an alternate types of compactness and then see the relation between them. So one is called limit point compactness, and this is actually the one that originally was the definition of compactness. And you may look at the textbook on topology by Munkers, who actually gave it this name, because after this definition fell out of favor in favor of the open covers and subcovers, then this definition had no name. So he at least said, at least let's give it a name which describes what it is. Yeah. Spacetimes of GR do obey the Heine-Borel theorem, I believe. And okay, let me come back to that. This is rather subtle stuff, and I don't want to get confused. Okay, so this is the definition is S is limit point compact if every infinite subset of S has a limit point in S. Okay, so if there's any infinite subset of S, then there should be a limit point inside S. And this is actually weaker than compactness. However, there is a result that which is really now it's really stretching everybody's knowledge of mathematics. But if a set is second countable and limit point compact, then it's compact. Okay. Now, what is second countable? Okay. So second countable is a space is one which has a countable basis of open sets. That means you can label the open sets by numbers n, as we have been implicitly doing. It would not be countable if you needed to label the basis by necessarily by continuous numbers. So countable means a basis of open sets. So there exists a basis of open sets labeled by natural numbers. Okay. There should exist a basis like that. Okay. From this point of view, it's pretty clear that all kinds of manifolds, differentiable manifolds, turns out with Hausdorff condition and so on, are all second countable. So we are not going to worry about being second countable. And in fact, Wald even argues that because the space-time is second countable and because of the way we defined open sets on CPQ, if you remember that O of U was an open set of CPQ if the paths stay inside U, because the U's are second countable, the O's are also second countable. Okay, at least he argues that under some conditions, but he doesn't give details. Okay, so we will assume that CPQ is second countable, and now we have an easier task ahead of us. Now we just have to prove, then we only have to prove that it is limit point compact. That's easier said than done, but it's a strategy and we are going to try and follow it through in the next 10 minutes or so. Okay. Yeah, everything. Yeah, we consider Hausdorff topological space and everything is second countable, including the open disk. Yes. Open disk actually is homeomorphic to the full plane. That's second countable. Yeah. In fact, we've proved that the open disk is second countable because we gave a countable basis for it, right? The disks, the expanding disks for n going from 2 up to infinity, that's exactly a countable basis of the open disk. Why is the assumption justified? I just said largely because the open sets of CPQ are inherited from the open sets of M itself, and M is second countable. But you can look up Wald, who says it a little bit more, who basically also says that it's provable but doesn't give the proof and refers you to Gerosh. So, the problem with these proofs is that if you prove everything, it takes forever. So it's almost like a non-compact space of lectures that to reach the limit point of an exact proof, never going to happen. I'm just going to assume it. It's not the hard, I believe it's not the hard part and it's not the insightful part of the proof. Limit point compact, on the other hand, gives us some insight. Okay, now we are trying to look for a limit point of a curve. So we better give some good definitions of limit points for curves. And so let's give two definitions, which are both interesting. By the way, in parentheses, I'll mention that Witten, instead of using limit point compactness, uses sequential compactness, which is another definition of compactness. And his line of reasoning is a little different. I have explained what I think is his line of reasoning in a footnote in my notes, but I'm not going to discuss it here because, again, it will stretch beyond the boundaries of this lecture. Okay. So a point P in a manifold M is a convergence point of a sequence So we are going to define two different things. We are going to define a point in the manifold, which will be a convergence point of a sequence of curves. Okay, a single point, not a curve. So this is not going to be a limit curve. This is going to be actually more like a limit point. And unfortunately, both convergence and limit points are needed. So let's give the definition first. If every open neighborhood O of P intersects X and mu of S, the X and mu of S is assumed to be the whole curve. Like as S varies, all the points you get, that's X and mu of S. So intersects this for all n greater than n, for some capital N. Okay. In pictures, here's a family sequence of curves like this. And we'll say that this point P is a limit point if every open neighborhood starts to intersect. So if this is the curve x1, this is the curve x2, then let's say this is the curve x10. Then after that, all curves x11, x12, and forever all come closer and closer to P, so that every neighborhood of P intersects infinitely many of these curves. Okay, intersects not just infinitely many, but it actually starts intersecting them. So you pick the neighborhood, okay, and then you find the capital N such that for a large enough, for small n greater than that, the curves come very close to P. They fall inside that neighborhood. For every neighborhood you pick is nothing but the delta epsilon definition of a limit, but applied to curves. Now, there's a slightly weaker condition that's also used, which is that P in M is a limit point of the same family of curves if every open neighborhood intersects infinitely many X and mu of S. Yeah. Now, this looks almost the same, but the difference is in the first case, I have an ordering of a sequence of curves. And the claim is that after some point, some n, all the curves are within the given neighborhood of P, or they pass through a given neighborhood. But here we are saying something weaker, which is that the open neighborhood intersects infinitely many of the X and mu, but need not be all the X and mu for sufficiently large n. Just to give you an example, a limit point may intersect only the even curves in a set. That is, for n even, it intersects them. For n odd, it doesn't for some reason. Then it's still a limit point, but it's not a convergence point. So limit point is a little weaker. Okay. Now, with these two definitions, we have the definition of limit curve, which is what we really want. A limit curve of a sequence of curves X and mu of S is a curve S, is a curve X mu of S. Maybe I'll put a bar to indicate that it's the limiting curve. No, I've called it, yeah, X mu bar, okay. If there exists an infinite subsequence of X and mu for which each point of X mu of the limiting curve X bar mu is a convergence point. Okay. So you can sort of see what this means pictorially. Basically, you have this family of curves. They're getting closer. They're tending to a limit curve x bar mu. And the idea is that every point on x bar should be a convergence point, which means that for some subsequence. So there's one subsequence for which every point of this limit curve is a convergence point. Okay. Now, I've defined convergence point and limit point, and I'm sure you're not going to grasp this right away. It took me a while to understand the difference. I defined convergence point here. I defined limit point here. It's not enough to have a limit point. It has to be a convergence point. Okay. And the reason is that a limit point could overlap with a finite subset of the curves, but the next limit point could overlap with a different infinite subset. The next limit point could overlap with a different infinite subset. Okay. And that isn't a satisfactory definition of limit curve. Okay. And now we have a theorem with this definition, which says that if, and this is almost the proof of our compactness theorem, if x n mu is a sequence of future inextendable curves having a limit point. I'll be very careful to say limit point when I mean point and limit curve when I mean curve. Having a limit point P, then there exists a limit curve also passing through P, which is also future inextendable. And what does this theorem say? This is actually pretty close to the compactness we want. If you like, it's the compactness not of a space of curves between P and Q, but of curves between starting at P and being future inextendable. Okay, and later we'll somehow get Q back into the game. I may even leave that for you as an exercise as it's getting late. So you have a sequence of curves. They don't have to pass through P, but P is a limit point of that sequence. So they get closer and closer to P, which is this point. And the claim is that then there's a curve from that actually passes through P and which is future inextendable and which is a limit curve of these other curves. Okay. Sorry that P got a little bit drowned out there, but here's P. So let's read it again. If x and mu is a sequence of future inextendable curves having a limit point P, then there exists a future inextendable curve passing through P, which is a limit curve of this sequence. So both it passes through the point, which is a limit point of the sequence, and it itself, the whole curve into the future, is a limit curve of this sequence. And I'll sketch how this is proved, and then I'll basically leave it to you as an exercise to take this and prove it for CPQ, which basically consists of putting back a point Q somewhere in this discussion. Okay. Yeah. Good. So the proof goes like this. First of all, P is a limit point. So P is given to be a limit point. So for every open neighborhood of it, O, it intersects for infinitely many of the curves in this sequence that we are given. Now we are going to choose our O in a particular way. This is true for any open neighborhood O. Now, Wald says, let's choose some Riemannian coordinates. In fact, he even says to choose Riemannian normal coordinates. I don't know if you know what are Riemannian normal coordinates. Normal are the ones which look most like Euclidean coordinates at a point. Okay, so there are coordinates which, you know, that any region of a point in a manifold can map to Euclidean space. But in particular, you can do it in a way that the metric looks like the identity at that point, with first derivatives vanishing and second derivatives not vanishing. Second derivatives can't vanish, but on a non-trivial manifold, but first derivatives can be made to vanish. So those are Riemannian normal coordinates. I think Gaussian normal coordinates are the same, I think. Yeah, you can check that. Yeah. Yeah. Now, Sambit, you asked if the limit, thank you. I'm glad you are all following. This stuff is like mind-boggling. If the limit curve passes through P, shouldn't it be a convergence point? This is a thing that I actually couldn't resolve. I'll request all of you to think it over and we'll revisit it next time. Maybe it should be a convergence point, but I'm using literally the words of Wald, and he says this is a limit point. I think it's enough actually, because infinite subsequence is allowed, then I think limit point is enough. We could have taken it to be a convergence point, but I think limit point is enough. Yeah. Okay, so where was I? In Riemannian normal coordinates. I don't know whether we really use, no, the limit curve actually passes through P. The limit curve literally passes through P. Actually, this theorem is too strong for us. It would be enough if all the curves pass through P, we could give the same theorem, and that would be enough. So passing through P is not a big deal. What we want is to show the existence of a limit curve. So actually what I'll do is next time we'll talk about it, and I might rewrite my notes in with a simpler version of this theorem. Okay, now back to these normal coordinates. So important point about these coordinates is that they are Riemannian, which means that they are coordinates of the manifold. This is all happening in a manifold. They are coordinates of Euclidean signature. So even though I'm working with a space-time, I can always put a Euclidean signature metric also on that space-time locally, and that's all I need. Okay, so you take those and take this O to be a ball of radius. What have I called the radius? R, around P. Okay, and as we've seen, this ball intersects all infinitely many or some infinite subsequence of this curve. So let's just focus on that infinite subsequence. Okay, now you can see sort of from the drawing that because these are inextendable curves, they are actually going for a small neighborhood O. They are not only going to intersect with the neighborhood, but they're going to pass through its boundary. And this boundary is here. This is a sphere. Okay, this is the spherical boundary of O. Because I've chosen O in certain coordinates, it's actually a ball, and this is the spherical boundary of O. And once these curves start passing through the spherical boundary, you'll see that at these points, there's an intersection. So I get a sequence of intersections of these curves with the sphere. And because a sphere is compact, that sequence has to converge. Okay. And whatever it converges to, I mark that and I say this point is on my limit curve. I'm basically building my limit curve. Okay. Now I draw a smaller sphere here. Again, there are infinitely many curves passing through that sphere, and there'll be a limit point that they reach, and I'll mark that point. And by drawing nested smaller and smaller spheres, I basically construct this stretch of the limit curve. Now, there's still a problem. It's not obvious completely that you'll get a smooth limit curve. You may get a jagged one, although it will be continuous. Okay, continuity, I think, is guaranteed because of the nature of these open sets, but it's not obvious that it will be smooth. And Wald, in fact, allows non-smooth curves in some of his discussions. So that's another subtlety that those who want to worry about can worry. Now, once we've constructed the limit curve from here to here, then we base ourselves here. So this limit curve, every point on it is a limit point of the original curve. So now I change my base from this point to this point and repeat. I construct a big sphere ball around it. By the intersection property, this curve will cut this thing at these points, and I'll reconstruct another stretch of the limit curve up to there, and I'll keep going. And because the original curves are inextendable, this limit curve will also be inextendable. So this is the proof. It's written in my notes. Infinitely many curves intersect. So let's give the ball intersect the boundary of O, which is a sphere, compact. So these intersection points have a limit also on the sphere. One boundary of O. Add that point to the limit curve, or include that point in the limit curve. Then repeat for nested balls. So there's a standard thing people do here. Smaller and smaller. A standard thing people do here is to take these balls to have various rational radii. Okay. And if you have rational radii, you can construct sort of rational points along this limit curve. And that's because rational numbers are dense in the real numbers, you can fill in the whole curve. So yeah, this is the method. And this proves that this theorem, which says that a sequence of future inextendable curves, which has a limit point, has a limit curve passing through that limit point, and which is also future inextendable. So we are very close to proving compactness of CPQ. And the last step, I'll just quickly say in words, is very easy actually. What you do is to take a point Q and remove it from the manifold. So for compactness of CPQ, you have to do a few more steps. So let's see. First, take P and Q both in the causal past, I minus. So there's a Cauchy surface. So we'll take, in fact, not only causal path, but we'll take it in the past domain of dependence of the Cauchy surface sigma. Okay. So here's the Cauchy surface. Here's Q, here's P. And this is the space of paths. Then at least Wall likes to argue that, well, first he argues it for compactness for this case, then he moves P and Q to the future, argues it again, that's trivial. Then he keeps P in the past and Q in the future and argues it again, which I'll leave to you as an exercise. So this will be enough. Okay. So now the idea is that if I remove this point Q from the manifold, okay, then the okay, so let me go through it in steps. Yeah, so we want to show every infinite family of causal curves from P to Q has a limit curve from P to Q. This will prove limit point compactness of the space, which I started with. Okay, so I'll remove, so I'll draw this infinite family. Okay, and I'll remove Q from the manifold. Remove Q from M temporarily. Then this family becomes inextendable. We've done this some time back. When you remove a point, things which ended at that point become inextendable. Okay, now we apply the previous theorem, which is the theorem on inextendable curves. This one, that if there's a sequence of future inextendable curves, then they have a limit curve which is also inextendable. Okay, so I remove Q from the manifold. Then I note that all the infinite family here of curves from P to Q become inextendable. Then they have a limit curve, also inextendable, for which Q is a future endpoint. Well, Q is not in the manifold. So if it were, it would be a future endpoint. Because it's not in the manifold, this limit curve is also inextendable. Now put back Q. If you put back Q, there are two possibilities. The limit curve either remains inextendable or it ends at Q. Okay. Now, remaining inextendable is impossible because the original curves never passed through the Cauchy hypersurface. Okay. Remember, when we took out Q, the manifold stopped being globally hyperbolic. But when we put it back, there's a Cauchy hypersurface, and the original curves never passed through it because I took P and Q in the past domain of dependence of sigma. So if these curves never pass through the Cauchy hypersurface, then nor can the limit curve. Therefore, it must end at Q. And that's the end of the proof. View. Okay. Could I repeat why choosing coordinates was necessary here? Yes. Thank you. That's a very good question. The reason choosing coordinates was necessary was that P being a limit point just told me that any open set around it would intersect these infinitely many of these curves. But if I choose a coordinates, then I have a concept called a ball. Okay. And the open ball is in particular an open set once I choose coordinates, because that's the topology on M. It's the standard topology. So for small, you see, the M may have weird holes, handles, and all kind of things elsewhere, but we are in an infinitesimal neighborhood of P. And then it's true that this ball is an open set and its boundary has spherical topology. Okay. And since the ball intersects with these curves, and since they are curves, they will hit the boundary, this yellow curve, the bounding the ball. And all these concepts, the ball and the yellow sphere bounding it, are coordinate concepts. They're not things that we have defined in the manifold, but they are well defined once I have coordinates. So they hit the boundary as they're going to the future. And because we know that in usual topology, open balls have boundaries which are open, which are spheres, and spheres are compact. Okay, spheres are closed and bounded in the usual definition, so they're compact, just like a circle. And in fact, it's drawn as a circle here. So I get a bunch of intersection points, infinitely many of them. But then every sequence, infinite sequence on the sphere must have a convergent subsequence. So there must be a limit point. And that limit point I find, and I say, look, that's 1 point. I've done all this to get 1 point of my limit curve. Okay, I say, very good, I got 1 point. Now I make another ball, which is smaller, and I mark another point of the limit curve, and I repeat until I have got all the points between P, where I started, and the boundary of my original ball. Okay, and then repeating is straightforward because I move P to be here. Okay, once I've constructed this, every point in this is a limit point of the original sequence. So I can pick this to be my limit point or something close to it if that worries you. And from here, I'll construct open balls and extend. So choosing coordinates was necessary to have a ball whose boundary is the sphere and to use the compactness of the sphere. Thanks, Krishna, and everybody for the great questions. I am exactly out of time, but I think one or two more questions are fine. I think it's fair to say this might be the toughest lecture of the whole 12 lecture series. I hope so. And let me also say, I mean, you should try, because these are things that people learned and understood. And, Hawking and Penrose, of course, Raychaudhuri, then Hawking and Penrose did their legendary work, not by shying away from this stuff, but if you don't want to do it, you probably won't be given an exam on this kind of thing, and you probably won't have to do it in future. And then you'll have to just remember that the space CPQ of causal curves is compact. That will be good enough to remember. Yeah. Can we do all operation integration after constructing coordinates? Integration, we don't exactly do integration. Okay, so I'll refer you to Wald first. See, this is Wald's construction. And by the way, Witten doesn't do it this way. He does it in a different way. But if you see, his way also has some kind of nested open sets to reconstruct a limit curve. He also constructs a limit curve, but he uses something more akin to sequential compactness. I am frankly confused between sequential, whether this and Witten's amount to limit and sequential. I've stated that, that's what I think, but I'll be happy to be contradicted. Sorry if you're hearing some noise, it suddenly started raining heavily here. Okay, what does dimension mean when we talk about CPQ? Yes, it's not a vector space. It's not a manifold, both are true. And therefore dimension doesn't mean anything. All I said was that if there was to be a dimension, it would be infinite, because a space of curves is an infinite dimensional sort of thing. Okay, you can think of that. There's something called loop space of a point, and you can Google that and look up loop space. It's an example of a space of curves which start and end at the same point. And that's infinite dimensional, and there's some mathematics known for that. So yeah, indeed, CPQ is definitely not a vector space nor a manifold, but it's a topological space with a topology that we defined. Yeah, this limit curve passes through the boundary of the causal diamond. Yes, I guess so. Yes, or bit of P and Q. Yes, it does. And in fact, though I've run out of time, my next step was to prove that because of all this, the causal diamond is compact, which is something we are trying to prove. And we'll do that in the beginning of the next lecture. Also, it's in the notes.
I just had a logistical question. Would you be taking the class next Friday as well? Because it's a holiday here, so I just need to know.
Your choice. It's also a holiday here, but I'm happy to take it. And I think people...
yeah, I just need to let them know that it will happen. So that...
Okay. So is there any vote not to have it? Because...
not really. I don't think so. But
okay, then let's do it.
Okay, cool. Thanks.
Yeah, thanks. Also, obviously, the Monday after that is also a holiday here, at least in Switzerland, and I'll be teaching on both days. Okay, all good. Thank you all. It's 5:32. I think this is not too bad considering what stuff we had to go through. And see you next time, Monday. Thank you all. Bye.